Hello everyone, my name is Len Chen Guanghua. My matrix numbers is AD190215. My section is section 6. Today, I'm gonna do presentations for our group assignments for Electricals and Electronic Technologies group assignments. Our chosen topic is Alternating Current Circuit Analysis. And the part I'm in charge is Introduction. So, the alternating current circuit is the circuit that is excited using the alternating sources. The alternating current AC is used for domestic and industrial purpose. In an AC circuit, the value of the magnitude and the direction of current and voltage is not constant. It changes at a regular interval of time. Thank you. That's all from me.
Hi, my name is Jiewei, matrix number AD190209 from section 6. So our topic is AC circuit. My part is example and calculation. So example is given and I will show the solution of this example. The example is a coil having a resistance of 7 ohm and inductance of 31.8 mH is connected to 230 volt 50 Hz supply. Calculate the circuit current, phase angle, power factor and power consumed. So from this question, we have the given data, which is R equal to 7 ohm, L equal to 31.8 times 10 power negative 3 H, V is 230 volt and the frequency is 50 Hz. Okay, so A is circuit current. Step 1 is, since we know I equal to V per Z and we don't know the value of Z, so and we know that Z equal to square root R square plus XL square and XL equal to 2 pi FL. So put in the value from the above and we get the answer XL equal to 10 ohms. Okay, step 2, since we get the value of XL, so just put in the value into the equation of Z, which is square root 7 square plus 10 square, and the answer is 12.2 ohms. Step 3, I equal to V per Z. So put in the value 230 volt per 12.2 volt ohm equal to 18.85 ampere. B, phase angle. The formula for us to get the phase angle is tangent negative 1 XL per R. From the above, we already get the value of XL, so put in the value tangent negative 1 10 over 7, so the answer is 55 degrees. For C and D is quite easy because we already have the formula. So for C, power factor is we using cos phi, which is cos 55 degrees, and the answer is 0.573. For D, which is power consumed, we have P equal to VI cos phi, so put in the value into it, and finally we get the answer 2484.482 watt. So that's all from me. Thank you.
Hello, my name is Liu Lucian. Now I'm going to talk about the example and calculation that related to the topic that we choose. In this question, the question is about an RLC circuit. Indeed, the RLC circuit is connecting a resistance of 30 ohms, an inductance of 100 mH and a capacitor of 40 microfarad are connected in series across RMS voltage of 50 volt and frequency of 60 Hz. The question asks to calculate the total circuit impedance, the circuit currents, voltage across each element, and also the power factor. This below are showing the diagram of RLC. First, we are going to calculate the total circuit impedance. In calculating the total circuit impedance, we are going to calculate the capacitor reactance and inductive reactance first. By calculating the capacitor reactance, we are using the formula 1 over 2 pi FC. In this question, the frequency is 60 Hz and the capacitor is 40 microfarad. From this equation, we can get the answer of the capacitor reactance, which is 66.3 ohm. After that, we are going to calculate the inductive reactance by using the formula 2 pi FL. The value of the inductance is 100 millihenry. From this equation, we can get the value of the inductive reactance, which is 37.7 ohms. Last, we are going to calculate the total circuit impedance by using the formula Z equal to square root R squared plus XL minus XC squared. By using this equation, we can get the answer of the total circuit impedance is 41.45 ohm. The second question is asked to calculate the circuit currents. By calculating the circuit currents, we are going to use the formula voltage divided by the total circuit impedance. From the formula, we can get the answer of the total circuit currents, which is 0.3619 ampere. After that, we are going to calculate the voltage across each element, which is resistance, inductance, and also the capacitor. By calculating the voltage across the resistor, we are going to use the formula circuit currents times the total circuit impedance. From this, we can get the value of voltage across the resistor, which is equal to 10.857 watt. By calculating the voltage across the inductance, we are going to use the circuit currents times the inductive reactance. From this, we can get the value of the voltage across the inductance, which is equal to 13.644 watt. Last, to calculate the voltage across the capacitor, we are going to use the formula circuit currents times the capacitor reactance. From the equation, we can get the voltage across the capacitor is 23.944 watt. For the last question, it's asked to calculate the power factor. To calculating the power factor, we are going to use the formula resistance of the resistor divided by the total circuit impedance. Thus, the power factor of the RLC circuit is equal to 0.723x.
Hey guys, my name is Min Gok Siang. My metric number is AD190228. So I'm going to present the discussion parts of our assignment, which is the application of AC circuit. For our part 1 is simple AC circuit. For resistor, the currents through and the voltage across are in phase. For capacitor, we find that when a sinusoidal voltage is applied to a capacitor, the voltage follows the current by 1/4 of a cycle. Since a capacitor can stop current when fully charged, it limits current and offers another form of AC resistance called capacity reactance, which has unit of ohms. For inductor in AC circuit, we find that when a sinusoidal voltage is applied to an inductor, the voltage leads the current by 1/4 of a cycle. The opposition of an inductor to a charge in currents is expressed as a type of AC reactance. This inductive reactance, which has unit of ohms, varies with the frequency of the AC source. So now for our part 2 is RLC series circuit with AC. So what is RLC series circuit? An RLC series circuit is a resistor, capacitor, and inductor series combination across an AC source. The same current flows through each element of an RLC series circuit at all points in time. The counterpart of resistor in a DC circuit is impedance, which measures the combined effect of resistor, capacitor, and inductors. The maximum current is defined by the AC version of Ohm's law. Impedance has units of ohm and is found using the resistance, the capacity reactance, and the inductive reactance. For our part 3 is the power in an AC circuit. The average AC power is found by multiplying the RMS values of current and voltage. Ohm's law for the RMS AC is found by dividing the RMS voltage by the impedance. In an AC circuit, there is a phase angle between the source voltage and the current, which can be found by dividing the resistance by the impedance. The average power delivered to an RLC circuit is affected by the phase angle. The power factor range from -1 to 1. Then this is our part 4, which is resonance in an AC circuit. At the resonance frequency, inductive resistance equals capacity reactance. The average power versus angular frequency plot for a RLC circuit as a peak located at the resonance frequency. The sharpness of width of the peak is known as the bandwidth. The bandwidth is related to a dimensionless quantity called the quality factor. A high quality factor value is a sharp of narrow peak. So finally, it's for our last part, which is transformers. Power plants transmit high voltage as low current to achieve lower ohmic losses in their many kilometers of transmission lines. Transformers use induction to transform voltage from one value to another. For a transformer, the voltage across the primary and secondary coils or winding are related by the transformer equation. The currents in the primary and secondary windings are related by the number of primary and secondary loops or turns in the winding of the transformers. A step-up transformer increases voltage and decreases current, whereas a step-down transformer decreases voltage.
Hello, my name is Laurila, matrix number AD190221. Now I will present about our group conclusion. For the signal audio case, the root mean square value of an alternating current is equal to the value of a constant direct current, which can produce the same heating power as the alternating current in a given current. We can find out the root mean square voltage by divide the peak voltage by square root 2. Then we can find out the root mean square current by divide the peak current by square root 2 in the same method. On the right hand side, that shows the graph of signal audio wavelength in the time domain. Since voltage is equal to product of current and resistance, voltage is directly proportional to the current. Hence, we can do an expression current I is equal to I0 sin omega t, where I0 is the peak current, omega is the angular velocity, and t is the time. For the phase difference between current and voltage, the AC voltage across the resistor and the AC current in the resistor are oscillating with the same sign function. Therefore, they are oscillating in phase. The phase difference between the current and the voltage is zero. Ohm's law can be applied for the effective currents and voltage. In a RC circuit, the current across the resistor and the current across the capacitor are not in phase. Hence, the maximum current is not the sum of the maximum resistor current and the maximum capacitor current. We move to RLC circuit. RLC circuit contains different configuration of resistance, inductors, and capacitors. In a circuit that is connected to an external AC current source, the picture in the left below shows the impedance triangle. We can use this triangle to find out the impedance. Then in our middle of the slide, let's show the method to find out the impedance in RL series, RC series, LC series, and RLC series. Then we move to the power factor is the amount by which the power derived in the circuit is less than the theoretical maximum of the circuit due to voltage and current being out of phase. The range of power factor is between -1 and 1.